Good morning or afternoon, everybody. I was about to say, great to see you all again, but I cannot see you as I am not there. However, I hope you are all having a fantastic day. So, I am going to be using these online lectures to try to keep up on top of everything during my paternity leave. I would be happy to introduce you to my baby if it was not 9:52 at night. However, it is 9:52 at night, so no baby. She is asleep. For now. Today, I'll be using a digital pen and Streamlabs OBS to record this lecture. I hope everything goes well. If you see anything wrong, visual glitches that I miss, or if I am too quiet, please let me know. I apologize for the poor audio quality. I don't have a professional mic. I only have a webcam that I use for recording audio. However, if it's a problem, maybe I will look into getting a mic. So, a quick recap. Last time when we left off, right, we were talking about scientific notation. Oh, and you know what? I'll give a quick fun fact for the day. In fact, Vikings, I hope I haven't told you this one already, believed that by crushing up the bones of powerful animals they hunted, they would actually, and mixing that with their metal, in forging, they would make stronger weapons. Little did they know, by adding carbon to iron, they were making primitive, weak steel. However, so it did make them stronger. However, it would be still much weaker compared to steel we have today. It's actually similar with meteorites, right? There's always the legend of making a sword out of a meteorite, which is somehow stronger than swords around. This would have been true in the Bronze Age, as we couldn't work iron yet. We couldn't smelt iron ore. So by making a sword out of the meteorite metal, which would have actually been pure iron and not iron ore, right, they could have made a sword that's stronger than anything they had at the time. However, it would not hold up to anything that was made in, like, the Middle Ages making actual steel. So, scientific notation. Scientific notation, right, as a quick reminder, is when you have a number that is between 1 and 10, and you get, and then it has decimals or no decimals. So, for example, 1.32, right? You make the number between 1 and 10, even if it's not. So if I had 132, I would rewrite it as 1.32. Then I can adjust by the number of decimal places I moved, in this case 1, 2, make that times 10 to the 2. Adjust it to be like the same number again. So if I multiplied 1.32 times 10, it would be 13.2. If I multiply by 10 again, it would be back to 132. Right? Since 10 squared is 100, 100 times 1.32 is 132. So really, when we write this, we are returning this number to its original form with the exponent. That's the point of scientific notation. It allows us to be precise with our sig figs. It also allows us to make very large numbers small and very small numbers large. All right, and then real quick for our sig figs, right? For sig figs rules, one through 9, those digits are always significant. Zeros are sometimes significant. A 0 that comes in between two other numbers is significant. Let's do sig. A 0 that comes before is not significant. Because technically, when I'm writing a number, I can write 10. If I really wanted, since a 0 was no value, I could put an infinite number of zeros in every other decimal place and every place before it to show that there's nothing there. We don't do that unless we're talking about decimals, because we don't need to. When we're talking about decimals, though, these zeros are needed to show me where the value starts. Right? They need to show me what the place value is. I don't have to worry about showing this place value here, since the place value starts from this point going out. So that really, place value starts from the decimal going this way and that way. So going this way, zeros are needed. Going that way, zeros are not needed. Right. Oops. Zeros afterwards all depend on if a decimal place is there. Both these zeros are significant because of the presence of the decimal place. The decimal place means that there is purpose to those zeros, and they were measured. Normally, right, even just this would actually be a way of saying that this was on purpose and this was measured or estimated, rather, since it's the last digit. This was estimated. Right. If I just have 190, however, that 0 is ambiguous. And obviously, I'm not just saying 1 and 9 are significant. It's 1 through 9. I just happen to keep using 1 and 9 throughout. But 1, 2, 3, 4, 5, 6, 7, 8, 9, all significant. This is ambiguous because it could be that the only reason I have it here is because I can't write 190 without the 0, but really only these are the ones that are measured and estimated. Or it could be that it is significant. This is why we also would use scientific notation. It would clear things up. You could have 1.90 times 10 to the second. You could have 1.9 times 10 to the second. You could have either, depending on what is or isn't significant. So when it's ambiguous, we assume it's not significant for math purposes, but you should try to avoid ambiguity. Right? Use scientific notation to avoid ambiguity. And as the last bit of our recap, I know this is a slightly long recap, almost going for 10 minutes, but I have been out for a while, so I want to make sure that you have this video that you can go back to with material you might be confused on. With our last bit of our recap, I want to talk about math with sig figs. Right? Again, addition, you take the number of decimal places, or subtraction. Remember, addition and subtraction are the same thing, right? Subtraction is literally just the addition of a negative number, and you can always rewrite that as that. So when you say 5 minus 3, you can think of that as 5 plus negative 3, and you get the same answer. So addition is really just subtraction. It's all about number of decimal places. So 1.30 minus 1.1 might come out to be, right, 0.20, but because I only have one decimal place here, I only put 1 in my answer. This is the hardest when we have large numbers, because we don't really think of numbers before the decimal as being decimal places, but they are. And so that's a little harder to see. If I have 1,000 minus 1, and these are all not significant, right now I have 999, except this was my furthest to the left decimal place. That's really what it is. It's the furthest to the left decimal place. So I have to round to that. And so I have to round to the nearest thousandth value. So according to sig figs, 1,000 minus 1 is 1,000. Unless, of course, you have 1,000 on the dot. If you can say with certainty you have 1,000, and you've measured out to this value, then you can say 999. And again, not exactly furthest to the left. I'm trying to think the best way to explain this. You look at all the digits that are significant. You look at the last significant digit in each number, and you go by which one is further to the left. So in this case, if you have 1,000 and it's ambiguous, this is the only one you know for sure is significant, and because it's further to the left, you go with this. But if you have 1,000 like this is the last one that's significant, and then with a 1, that's the last one that's significant. And so you go for the furthest left, which is furthest left of the last significant ones, which would be the ones place. Most of the time you're not going to be dealing with this. However, this is probably the hardest bit to do math with. And then we have our combination, then we have multiplication and division. Again, division is just multiplication of fractions, right? 5 divided by 4 is the exact same as 5 times 1/4. So really, again, they're the exact same thing. For these, you just go fewest sig figs. So again, let's actually go with that previous example. Let's say 1.0 times 1.3, well, let's say 24. No, that doesn't help. That's the same number. 1.32. The answer here would be 1.32. We have 4 sig figs here, 1, 2, 3, 4, and 3 here. So we're going to take 3. However, if we only had (1.0) times 1.32, we'd only have 2 sig figs. So instead of being 1.32, we'd end up with 1.3. Or if we had 1 times 1.32, we would be rounding to 1 sig fig. So we'd get our answer of 1.32, and we would round it to the nearest single sig fig, which we would end up rounding down because it's less than 5 to just 1. So according to significant figures, 1 times 1.32 equals 1. And again, it's easy to look at this and say, well, this is a dumb approach to math. It's more inaccurate. And that's kind of the point. If you only have a single digit that you have measured, and really the last one should be estimated and not measured. So if you're looking at a scientific number that just says 1, that is completely purely an estimate. And so the reliability of that data is not much, right? That is not great data. When you combine them, you literally just apply both the rules. We would look at this and we'd say, I'll say 5.04 here. So we would apply, right, the multiplication first. 3.2 times 2.00, we get 6.4 because we have 2 sig figs. No, this one's not a great example because there's no rounding there. I apologize. Let's imagine there was rounding for a second, though. What we would do All right, let's imagine there was rounding and this dragged on for like, I don't know, 4 digits. You'd write all 4 down and you'd do the math with that. But you would make a note that this thing only has 2 sig figs, and for the addition part, you would make a note that it only has, right, it only goes out to the 10th place. So then when we do the 5.04 plus 6.4, right, even if the math is out to 4 digits here, you add it up and then you round to the 10th place. In this case, we would get 11.44, rounding to the 10th place. Because of this, we drop that, we get 11.4. All right. That's a recap of what you've learned this chapter so far. And a quick recap, again, if you're having trouble with that stuff, please refer back to this video. Now, I want to go over something new. I want to go over unit conversion. A lot of you have probably been converting units for a lot of your life, right? And most of the time we use simple unit conversions that we mostly do in our head. For example, 12 inches is equal to 1 foot. If you have 3 feet, you would just multiply that by 12 and get 36. Or if you looked at 36 inches, you just divide that by 12 and get 3 feet. I'm going to teach you a method which is showing out the math for doing that. A lot of people find this hard. I'm going to give you easy questions to start that have things like this that I want you to show out the math for, because I want you to get used to the math before we get to the hard questions. The best thing you can do for yourself all year is learn how to do this. It will make all the math for the rest of the year much, much easier. So make sure you learn how to do this. Right, we quickly do these in our head because we're used to converting them. But the actual math for this looks a bit like this. Say 12 inches times 1 foot. Let's say we have 36 inches, right? We gave the example of the 3 feet. So let's say we have 36 inches times 1 foot over 12 inches. This is what's called a conversion value. And the reason we can write this and multiply this actually makes a lot of sense if you think about it, because this is the same thing. If these are equal to each other, then this is the same thing as multiplying a number by 1 over 1. Ask your math teacher if you don't believe me. You can multiply any number by 1 over 1 because it won't change the value. However, the point of unit conversions is we're not changing the actual value. 36 inches and 3 feet are still the same length. We're just changing the unit it's expressed in. So we're multiplying by 1 over 1. However, we've taken 1 and we've split it up into 12 smaller parts on the other side. And so the number might change, but the actual length doesn't. Any unit conversion you have, or established relationship you have. So for example, if you're looking at the amount of something in your blood in terms of grams per liter, you could use that as a relationship, and I could say, oh, well, in 2 liters of blood, I have this many grams of a chemical, right? Any established relationship that you have can be used as a conversion factor. And let's do the math out. 36 times 1 is 36. Divided by 12 is 3. But now we also get into the units. Now for this one, it's obvious to us. 12 inches are in a foot, so we don't really think about it. But as we get into more and more complicated units that you are not familiar with, this part that I'm about to explain is going to be crucial to understand. And I really, really mean crucial. If you don't get this now, please send me an email, set up for a one-on-one Zoom call after school, because if you don't get this now, like this, it's going to come back and bite you in a couple months, and it's going to make doing the math miserable. When we do this conversion, units are actually a lot like variables. If I said that x, and we multiplied, I had x, and we multiplied x by, x, and I multiplied that by y over x, my x's would cancel out, and I'd be left with y. Units work in the exact same way. I have a unit that I'm dividing by another unit. Those cancel out, and I'm left with my new unit. So x divided by x gets rid of the x's, and you're left with just the y. Inches divided by inches gets rid of the inches. You're left with just the feet. Again, this is absolutely crucial. Actually, we can think about this in other places that we see it. You measure the length of a box or of a square in inches, and you measure the width in inches, and you multiply them together, and you get inches squared. You are multiplying the numbers together to do it, but you're also multiplying the units, and so the units are squared. This is just how units work. So I'm going to put up some problems. I would like you to pause the video and try solving them, and then I will go through and solve them. Alright, I'm going to leave these, pause the video, try to solve it. Okay, welcome back. Let's go through each of these problems. 14 feet being converted into inches. We would have 14 feet being multiplied by, so this time for the conversion factor, we want feet to be canceled out. Before, we had the foot on the top and the inches on the bottom, because we were canceling out inches. However, if both of them are equal to 1, it doesn't matter which one's on the top and which one's on the bottom, beyond canceling things out. So now, we're going to put the inches on the top and the feet on the bottom. We have 1 foot and 12 inches. So it ends up being 14 times 12 divided by 1. Do the math here. I'll try doing the math in my head real quick without it. It should be 144 plus 24. So it should be 168. Let's check that real quick. 14 times 12. Yep, 168. Inches. All right, now let's look at inches into yards. Shoot, actually, let me, shoot, okay. I was trying to just highlight one small group, but I must have misclicked. 28 inches into yards. For this one, we actually have 2 conversions in a row. First, we have inches into feet, and then feet into yards. Technically, you could just go straight there, right? We know that 3 feet is 1 yard, and therefore 36 inches is 1 yard. So we could use the direct comparison there, but let's take the double conversion, because that is also a skill you'll be using throughout the year. So 28 inches, and our first conversion factor is going to be into a foot. 1 foot per 12 inches. This would cross out our inches and leave us with feet. But we want to go to yards, so now we'll do, in addition, it's 1 yard per every 3 feet. We're canceling out our feet, and we are left with yards, which was our goal. So, if we have 28 divided by 12, divided by 3, we get 0.77, technically, it's 7 repeating, but I actually said at the start that it's 28 inches, which means 2 sig figs. All right, our last one was 100 grams to kilograms. The conversion factor between grams and kilograms is 1,000 grams per every 1 kilogram. This is the metric unit, which we will be covering shortly. If not in this video, then in the next. So, if we want to convert, we need to divide by grams. Our conversion factor is going to be, we want the kilogram on top because that's the thing we're trying to get. And we want grams on the bottom because that is what we're trying to cancel out. So this way we can cancel out grams and we're left with kilograms. In this case, 100 divided by 1,000 is 0.1 kilograms. Now, let me grab textbook to just check and see if there was anything else I wanted to cover with this. With this, I'm going to be giving you a unit conversion homework that will be posted on Google Classroom. Please feel free to refer back to this video as you're doing the homework. We covered conversions and multi-step conversions. Was there anything else I wanted to cover before we move on? Yes. Sorry. Last thing is units raised by a power. I mentioned before that, right, remember, if we multiply inches by inches, we end up with inches squared. If we want to do unit conversions, it's going to be similar. So, converting from one unit to another, we have 1 centimeter is equal to 2.54, sorry, 1 inch. my apologies, is equal to 2.54 centimeters. Therefore, 2.54 centimeters all cubed is equal to 1 inch all cubed. And let's think about what exactly I'm writing here. If these are the same length, then if I have a 1 inch by 1 inch by 1 inch cube, and I can never quite draw this back line well. That's a bit better. If I have a 1 inch by 1 inch by 1 inch cube, then I also have a 2.54 by 2.54 by 2.54 centimeter cubed. However, just equating these doesn't exactly work. So when we cube the 3, so if we're dealing in cubic values, we have to cube the conversion factor as well. So if I'm saying I have 50 centimeters cubed, and that's my volume, and I want to convert it to inches, I would have to say, okay, well, 1 inch is equal to 2.54 centimeters. And if I'm dealing in cubic, I'm going to cube the entire thing, number and conversion value. 1 inch cubed is just 1 inch, but 2.54 cubed is 16.387. Let's do 16.39. 1 inch cubed over 16.39 cubed centimeters cubed. So you would divide the 50 by the 16.39 after you have calculated that. That's how we do, again, squared, cubed, any kind of power. You cube the whole conversion factor. And normally, you won't find lists of conversion factors between centimeters cubed and inches cubed, because you could just do quick math with the conversion factor that you are given. All right, let me check the time of the video at this point. We are up to 33 minutes. So we have 10 minutes or so left. The last thing I would like to talk about today, which actually maybe I should have already talked about, but check if I accidentally skipped it. That's okay though, is units. Specifically, our SI units. So, SI equals System Internationale, made by some Parisians during the French Revolution. You see, people realized that everybody was using a different method of measuring things. Part of this was actually so you could scam some people. You couldn't really scam locals this way, but if you had travelers traveling through your town and you told them that you measured out food and cost by some unit they weren't familiar with, then, well, they might have felt like they were ripped off by a bad economy. They didn't feel like they were scammed in terms of actually lied to. And so having separate units for places was a way to get away with scamming people. The French government decided to create the Système Internationale to try to put a stop to this and to further scientific research. They created base units for various things that we can measure to try to standardize everything. This is often called the metric system, but not every base unit is really involved in the metric system. So, the first thing we have is the kilogram. This is the SI unit for mass, and what we tend to measure mass in. In chemistry, we tend to use kilograms or grams, sometimes milligrams as well. So the Système Internationale, the SI unit for mass is kilograms. The SI unit for length or for distance is a meter. Oops. It's supposed to be a TH, not an HT. The SI unit for time is a second. And the SI unit for energy is something called a joule. I'm trying to think if I am missing any important SI units. And really, the most important ones are just, for now, are these first three for our purposes. We'll talk about energy when we get to energy. So, with these, we also have prefixes. Now, I will say, in this, right, a second, oh, and sorry, our SI unit for temperature is something called a Kelvin. A Kelvin is essentially only used for science, and it is defined by being where 0 Kelvin is absolute zero. A temperature at which there is no energy and all movement stops. It is a theoretical temperature that I don't believe could actually be reached. We've gotten within a few decimal places of it, but we can't actually get to it because actually stopping all motion is pretty difficult. Let's talk about our prefixes, though. And again, let me check the time real quick. 38 minutes, okay. We have prefixes that are used to tell us how large or small a unit is. So for our prefixes, we have just a base one in the middle. It's not actually called base, it will just literally be nothing. Right? So like a gram, nothing editing that. Then going up, and I'm going to write the unimportant ones in red and the important ones in black. And if they're unimportant, I'd say like, if you're later on to the point where you're a professional scientist, yeah, you should probably know them, and they will be used in niche fields by certain people. But for our purposes, I'm only going to ask you to know the ones I label in black. So first we have deca. So for example, and this is 10. So a decagram, for example, would be 10 grams. Yeah, let me rewrite that in a less awful way. Sorry. Actually, I'm going to get rid of the gram here. So I'll do an example over here. Here we go. Example, gram. Then we have deca, which is 10. Example, decagrams. So 1 decagram would be 10 grams. We also have hecto. And also deca is much like decade is 10 years. Hecto. Actually, let me move this off into the corner here. Let me shoot. Sorry, I'm trying to move this up a little bit. Hecto is 100. An example, that would be a hectogram. An important one is kilo, which is 1,000. For example, the kilogram, or a kilometer, right? 1,000 meters. That's a good one to know. These ones are unimportant, but at the same time, actually, you probably should know them for computer purposes. Oh, and I'm also going to show the symbol here. Sorry, I'll just show all those in black. Deca is DA. Hecto is H. I guess I'm not, since right, the base one obviously doesn't have a symbol. Kilo is K. Then we have mega, which is 10,000. And actually, one place you probably know this is a megabyte. A megabyte of data is 1,000 bytes. Now, 1 byte is 8 bits. Well, it depends on how you look at it, right? There are megabytes and megabytes, and they have like pretty much the same name, but it's technically 2 different things. So, going off of a metric unit megabyte, it's 1,000 megabytes is a byte. Or so 1,000 bytes is a megabyte. But in computers, it's actually 1,024. And I can go into the explanation of that sometime if you want me to ask me in class, but it's a bit weird. So anyway, think of this, a megabytes. It's about roughly 1,000 kilobytes. Or sorry, yes, for this case, it's a jump up from each one. So in this case, it would be 1,000 kilobytes makes a megabyte. 1,000 megabytes makes a gigabyte, and 1,000 gigabytes makes a terabyte. And that's where it really jumps up by 1,024, but that's kind of where these come from. So we have giga, right? You'll recognize these from computers. And then tera. These make, right? Oh, I'm sorry. This isn't 10,000. This is, I apologize. this is a jump up of 3. So that's also 1,000 increase from that. So that's 1,000,000. This one is 1,000,000,000, and this one's 1,000,000,000,000. I apologize. So now we also look at going down. This one I'm also going to put under unimportant. D is deci, as in a decimal, a fraction of 10. And this is 10 going down, or 0.1. One place you might see this is a deciliter. That's often the volume of blood that we talk about when we're talking about certain amounts of things in our blood, is deciliters. We also have centi, as in centimeters. I'll make this one an important one. C for centi, which is 0.01. After that, we have another important one. M for milli, 0.001. Milligrams or millimeters are extremely important for measurements in chemistry. Beyond that, we jump down an extra 1,000. And although these are really important for certain fields of chemistry, especially things that I used to do, I'll put micro. Let me move that over real quick. In red. This is, again, it is smaller than this, so it's 0.0000001. It's about 1,000th of that. This uses a Greek M called a mu as its symbol. So you might see a mu meter, or a micrometer, right? Or a microliter. Oh, I'm sorry, I forgot the SI unit for volume. I'm sorry. Liters. Add that as an addendum to your SI unit notes. All right, now we're running out of time here, so I'm going to go quick. So, nano is N. You probably know this from things like nanobots, right? This is, I'm just going to, instead of writing out all the zeros, 1 trillionth. So divide by 1,000,000,000. So at some point, looking at all the zeros just becomes hard to look at and not helpful anymore. And then finally, we have femto, which is 1 quadrillionth. Oh, I'm sorry. I skipped one. Nano is 1 billionth. I skipped pico, which has a P, which is the trillionth. I apologize for that. And the femto is 1 quadrillionth. So nano is going to be on the size of a molecule. Pico is going to be the size of a bond between two atoms and getting closer to the size of an atom itself. And femto is just incredibly small. That's going to be like a fraction of the length of an atom. If we're talking about distance, we're talking about meters, femtometers, things like that. However, a femtosecond is actually the amount of time it takes for a bond to form. And by using a laser, that pulses every femtosecond. Femtosecond lasers are a thing. They cost a ton of money. You can actually, using very complicated math, measure a femtosecond. Or you can measure a bond being formed in the femtosecond time frame. All right. I am going to leave that there, I think. We're probably just about the end of class. You might have gone over a tiny bit. The last thing I want to say is just for unit conversions for these, just use this graph. If I want to convert grams to milligrams, just look down and you can say, okay, going from a base of 1 to 0.001. So that's 1,000 milligrams in every gram. Right, and so use this, you can say 1,000 milligrams per gram, but you could also write this as 0.001 grams per milligram. And that can be the conversion factor you use for unit conversions. If this is a little sloppy, just look up a metric unit prefixes chart, and that will have all of this. All right, have a great day, everybody. I'm going to finish recording this and upload it to YouTube.